In this problem, we want the largest one to be bigger than 3/4. So this is the situation. I made this diagram here. So the top point, the red dot, will move around randomly, and the bottom one will also move around randomly. So, but we want the cases in which either one is bigger than 3/4. So that can be translated, say it's bigger than 3/4, the maximum of them. That automatically means the minimum was less than 1/4, because there are only two areas, right? So we want this gray area to be large, such as like this, more than 3/4, or the same gray area is less than 1/4. What's the probability that those two cases would happen out of all possibilities is what this is asking. And another thing is the area of this gray area is the average of these two coordinates. I want you to see that. Because this is trapezoid, you see? Like that. This is the base. These are the heights. So if I average the x coordinates of these 2 points, because the base is 1 here, it will automatically be the area of the trapezoid. There are many ways to do this here, but we are basically dealing with P1 and P2. So what I want to do is a plot 3D, under which I want to plot the mean of P1 and P2. I think I need to use a curly bracket here. Okay, so that's my height, and my P1 goes from 0 to 1, and P2 goes from 0 to 1. And it looks like this here. So in which I want to see when the area is either less than 1/4 or higher than 3/4. So that I can compare them. I did this here. So I want either this area or this area, right? So how big are those? This looks somewhat confusing, so I will just get rid of this one here and then plot this one. So that's the 3/4 here, and the slanted one is the area of the trapezoid. Okay, so we want to know when the trapezoid's area is bigger than 3/4. So where are those intersections is the question. Here we can just solve by inspection here. See, this inclined one is going from 0, 0 to 1, 1. So this is 0.5 in the middle here. And this one is also middle of the middle. So this height is 0.75. So that's where that is. And this is cutting in the middle here. So this length is 0.5. And this length is 0.5. Notice that I'm not looking for the area of this yellow one, the brown one. That would be misleading because it's slanted. The area is larger. We are looking for the area of the blue one under this brown cover. So it's a 0.5, 0.5. And then this is a triangle. So we got to divide by 2. But there's another one underneath. Remember, it had to be either smaller than, larger than 3/4 or smaller than 1/4. So there are 2 of those. So I'm not sure if I'm making sense. So it's a 0.5 times 0.5 over 2 is the triangle area of each. And then there were 2 triangles. So therefore, this is the probability. Another way is to use the Monte Carlo method. So P1 is a random number. Okay, when I do this here, automatically picks any random number from 0 through 1. Or I can specify it. So that's P1. So I can produce many of those. So shall we produce, say, 100 of them? I got that. And then I want to produce P2, which is same story. I can have 100 of them. Okay? But there's an easier way of doing it. I can produce P1 and P2 together. So I can say P1, P2 by saying I want to produce 100 of them, but I want it to be a pair, like that. Then I will have 2 numbers each. So this is my P1 and P2. So what would be the area of the trapezoid? It would be the mean of those, right? So the mean of P1 and P2 would be the mean of each number that I'm producing, like that. So these are the means here. So now the question is, how many of them are above 0.25 and below, above 0.75, 3/4, or below 1/4? So let's select them. Of this mean P1, P2, I want the number to be either less than 1/4 or number to be larger than 3/4. And it will pick those numbers for me. Okay, so I need not see this here because I know I'm getting 100 numbers. But what I'm interested in is not the numbers, but how many of them I have. (22), roughly 25, you see. So what I want to do is that I will combine these here now and get lazy. So I will say sample is 100, and I'm going to get that many of them. And then I'm going to divide by the sample here. So this, and I'm going to turn this into a numerical value so that I can see the probability. So it's 28%, it says. If I do this, 18, 21 is fluctuating wildly because I don't have enough sample numbers. So if I make 1,000 samples here, what do I get? Oh, if I do it again, you see it's dancing around 0.25. You can never be sure because this is a random process. So the Monte Carlo method is used when it's expensive to evaluate completely, which is our case because I cannot evaluate every single real number between 0 and 1. So I'm doing some. So let's do 10,000 here. The number gets closer to the 0.25, and you see it doesn't fluctuate that wildly. It's near there. You see, it's never 0.3 or it's never 0.7. It's around there. So if I increase the sample size, remember how wildly fluctuating it was? Look at that, 2.1, 2.1, 1.7, 2.8, 1.8, see? But as you increase the sample numbers here, you will see it gets awfully close to the actual probability. So you can have some sense. Now let's do 1 million. And it takes longer, you see, running. But the number gets closer to the reality. So this is the sampling. So the larger the sampling you have, the more accurate your prediction is going to be. So, for example, if you're doing the vote counting or the polling before an election, you need to have large numbers to have it. This is the confidence interval changes. So if you did only ask 10 people here, when the reality was to a quarter probability, you get this twice or much smaller numbers. You get all kinds of numbers. Usually half. So you see how wildly it fluctuates. But when you have this kind of large sample, you cannot go far. You'll be very near the actual number.